So hello everyone. So we're going to do what is one of my most favorite examples in 121, which is the motorcycle in a sphere. Okay, so I don't know if you've seen this before, but like a maybe Cirque du Soleil or something like that. You've got this giant metal mesh sphere, and you open a hatch down here, and the motorcyclist comes in. You close the hatch, and then the motorcyclist zips around, say in a vertical circle like this, or zips around in horizontal circles and stuff. And so it's a really sort of fun problem. And there's actually a lot of really interesting sort of rich physics going on in this problem. So what we're going to do is we're going to focus on, the simplest possible case. As always, what we do as physicists is we look out into the universe, we pick an example, and we simplify it as much as possible so that, it's doable and we can understand it in great depth. Okay, that's the idea. So I guess there's sort of two different cases that you can think about. You can think about a motorcyclist zipping around in a horizontal circle like this, say in the bottom half of the of this sphere. But you can imagine that problem is very similar to the car going around the banked curve. The difference is that the angle of the bank changes. If you're close to the bottom of the sphere, it's nearly a zero bank angle. But as you go to circles higher up, then the bank angle gets steeper and steeper. And then you can ask questions like, I wonder if that motorcyclist could zip around right at the equator where the bank angle is like this, right? And what if could that motorcyclist go in a circle above the equator, zipping around like this? You can ask questions like that. So there's some notes on that. I remember I think I made last year some notes on going above, but I'm not sure they're posted. But anyways, give it a try and try to work that out on your own. Could you actually go above the equator? But anyways, we're going to focus on the other example, which is a vertical circle. Motorcyclist zipping around like this. And we're going to try to keep it as simple as possible, and yet you'll see there's still a lot of rich physics. Okay, so here's what the picture looks like. So we've got a big sphere. Let's put it right here. So there's a sphere like this. And this is the equator. And here is okay, so this is the circle in which the guy's zipping around. And so let me actually do that in a different color. Okay, so this is the bottom of the sphere, and so the guy's going to come from the bottom of the sphere, go up a line of, these are latitudes, longitude, and go up a line of longitude like this, up to the North Pole, go down, and then go down the opposite circle of line of longitude. Sorry, longitude. These are longitudes. Those are latitudes, okay? So we're going up a longitude and down the other longitude on the other side, and we're zipping around like that. Okay, and so this is our sort of situation. We will take, so this is the center of the sphere right here, and so we'll draw a dashed line to the bottom, the south pole of the sphere, and at some instant of time, so this motorcyclist is zipping around like this, at some instant of time, let's suppose the motorcyclist is at that point, and we say, we'll put in the mass of the motorcycle and the rider, and this thing is zipping around, and let me see, so there's the radius. So this is circular motion, and so the motorcyclist always remains the same distance r. The radius r of the sphere is the radius r of that vertical loop, that vertical circle, and we will take the angle theta to be measured from the bottom point on that circle, from the south pole of the sphere. So when theta is 0, the motorcyclist is just passing through the south point of the sphere, and then this is theta equals 90 degrees, theta equals 180 when they're at the North Pole, theta equals 270 when they're at the equator on the other side of the sphere, and then coming around to theta equals 360 or 0. Okay, so they're zipping around like that. And what else? And so we'll also indicate the speed. So there's a speed v that we're zipping around at. Now, here's the thing. That speed v, of course, could be changing. But to keep things as simple as possible so that we can really work it through in detail and understand it in depth, we're going to take the simplest possible case where we're going to assume that the speed v is constant. That's a central assumption for this whole thing. Okay? And so what that means is that because it's uniform circular motion, no matter what the forces are that are acting on that motorcyclist, and they would include gravity pulling down, they would include a normal force pointing towards the center of the sphere, and they would include static friction, because we're assuming the wheels are not spinning. Okay, the wheels are always maintaining traction. Okay, so there'll be gravity, normal force, static friction, so on. All those forces at any instant of time, no matter where they are on that circle, all of those forces have to add up to a force that points directly to the center of the sphere. And so sometimes we get a little confused about that. And so let's just take the simple example of a horizontal circle. So we got some kind of an airplane, say, moving around in a horizontal circle, or anything moving around in a horizontal circle. And you think, oh, there's gravity pulling down. Yeah, there's gravity pulling down, but then there must be another force pushing up to cancel the force of gravity so that there's no net force in the vertical direction. And if you start at rest in the vertical direction, you stay in that at rest, and you stay at rest in the vertical direction. Okay, and so you're moving in a horizontal plane like this. So gravity pulling down, something else canceling out gravity. Maybe you're going around on the surface of a table. Okay, but then on top of the gravity and the vertical force canceling gravity, you need that that horizontal force, that force directly towards the center. And that's true no matter what plane that circle is in. Horizontal plane, force is always directed towards the center of magnitude mv squared over r. If it's a vertical plane, forces are always towards the center with a magnitude mv squared over r. Okay, super important point to understand about circular motion. Okay, so whatever the forces are, it must be true that when we add them all up, sum them all up, they must be a force of magnitude v squared divided by r, mv squared divided by r, mass times the centripetal acceleration, and in a direction towards the center of the sphere. So in the negative r hat direction. That's that direction at this point. At that point, it's that direction. At that point, it's straight down, and so on. Okay? So that's crucial. Some of the forces have to add up to that if v is equal to constant. Remember, if the speed is not constant, then there can be an additional component of acceleration, and hence you need an additional component of force that is tangential to the velocity, increasing the speed or decreasing the speed. But we want the speed to be constant. Okay, that's crucial. Now, you look at this problem and you say, ooh, that's a problem in three-dimensional space. That's going to be complicated. No, it's not. It's a problem in two-dimensional space. This entire circle, this loop, is in a vertical plane. Okay, and so it's really two-dimensional motion. And so we will take sort of a side view of this, and we will put the circle here. Okay, so it's really a two-dimensional problem, just circular motion in a two-dimensional plane. So let's draw that, say, over here. So this is, yeah, there should be enough room. So this dashed circle that I drew is this orange circle seen side on. Okay, and the motorcyclist, this is the bottom of that sphere. That's the South Pole. That's the North Pole. So that's the center of the circle. And this is angle theta equals 0. And when the motorcyclist has passed through, say, 30 degrees or 45 degrees or something, there may be, say, around, what would be a nice place to put this, say, right around here. Okay, and so now at that point, the motorcyclist is at an angle theta from the South Pole, from the bottom of the circle, and they're moving with some speed v, and we're going to keep that speed v constant as the motorcyclist goes around. Oh, I should also mention that, of course, the motorcyclist has some physical size. Maybe in this sphere, the motorcyclist is this big. This is the top of his head. That's the bottom of the wheels. And they're going around like that. That adds some additional complications. You need to think about, well, where is the center of mass of that system? And, oh, wait a minute now. That guy is actually, it's a massive object which is rotating. And if his speed is changing, then his rotation rate will be changing. So you need torques and all kinds of stuff like that. That's for like the latter third of the course, later on in the course. We're not going to do that. So we're going to try to keep things as simple as possible. We are imagining that the motorcyclist is of negligible size compared to the size of the sphere. Okay, so in physics, we get really used to making simplifying assumptions like that, which don't detract from the basic physics, but make the problem solvable exactly, and so we can understand it deeply. So we just really have a point mass that's zipping around like this. Okay, and that point mass has no moment of inertia, and so we don't need to worry about that kind of stuff. Okay, very good. So what else? And the sphere, the circle here has a radius r. Okay, great. And what else? Okay, so now we need to think a little bit about the forces that are acting. So for one thing, we know that no matter where this person, where this motorcyclist is in this circle, this vertical circle, no matter where they are, the force of gravity has magnitude mg and is pointing straight down. Okay, no matter where they are, that force is always there. Okay, so there's that. So this whole thing is taking place in, I should have mentioned, in a uniform gravitational field G. Okay, and so there is, I'm going to draw sort of the free body diagram right here on this circular trajectory. So we have a weight, which is the vector mg. Okay, great. And then we know that this guy is whipping around this sphere, and as that guy is whipping around, you know that this guy is pushing into that metal sphere, okay, as he goes around. Okay, and so that pushing in to that metal sphere is going to compress the atoms, and then those atoms will push back, and so there will be a normal force. So the sphere will exert a normal force towards, always perpendicular to the velocity towards the center. So there's certainly going to be that force that's present. It's going to be a normal force. That's going to be partly responsible for the centripetal, or the center-directed force, of magnitude mv squared over r. Okay, so there's a normal force that's acting. Okay, but there's also going to be a friction force. Now let's talk a little bit about this friction force. So first of all, suppose that the motorcyclist just coasted around this circle. Okay, so as they were coming down, as they passed through the South Pole, suppose they're moving really fast, and then they put their motorcycle in neutral. They don't use the engine, rev the throttle, or they don't use the brakes. So they're just coasting. Okay, then as they pass through the bottom, they're moving fast. But then as they start moving up here, obviously they're going to slow down. So they're going to slow down, slow down, slow down, slow down, but they'll be moving slowest at the top of this vertical circle. And then on the way down, they're going to be picking up speed faster and faster and faster and faster and faster. Fastest down here, slowest up here. So they're going to be whipping around here and then slow, and then whipping around here and then slow. Okay, that's what's going to happen if the motorcycle is just coasting, not using the engine or the brakes. But what we want to demand, to keep things as simple as possible, and actually to make it interesting, is we're going to try to demand, or we will demand, that the speed remains constant. Okay, which means that as this motorcyclist passes through the bottom, their speed is whatever it is. In order to prevent them from slowing down, they're going to have to crank up the throttle and use the engine. Okay, and then when they're on their way down, they're going to have to use their brakes to keep from speeding up. Okay, so engines on this side, brakes on this side. Okay, now let's think about this a little bit, because this is tricky. So first of all, there's going to be, the sphere is going to exert a force of friction on the tire, the piece of tire that's momentarily in contact with the sphere. So let me draw that sort of down here. I'm going to take this little section and I'm going to blow it up here. Okay, this is that point over there. And what I'm going to draw is the motorcycle tire. So the motorcycle tire is like this. It's a chunk of rubber, like this. Okay, and we're saying, obviously, the motorcyclist has to apply engine power, right, on the way up. So he's on the way up here applying engine power. What does that mean? Well, if you apply engine power, what the engine does is it exerts a twisting force on the wheel this way. The wheel is rolling this way, and you want it to twist. You would exert a twisting force, or what's called a torque. We'll talk about that later. So the engine exerts a twisting force on that wheel. Now, it's very important to remember that we're going to assume that whenever a chunk of rubber there's this wheel going like this. Whenever that chunk of rubber hits this sphere, it is always remains not slipping. We're maintaining traction all the time. So as the wheel rolls up, the wheel never slips like this. There's no sliding happening. Okay, the wheels aren't spinning. The wheels are rolling along the inside of this sphere. So every time a chunk of rubber hits this sphere, when it's in contact with the sphere, the rubber and the sphere do not slide relative to each other. If they were sliding relative to each other, we would use kinetic friction. Because they are not sliding with respect to each other, we're talking about static friction. Okay, that's the one important thing to say. So now I'm going to take a little chunk. This here represents a little chunk of the piece of the rubber of the wheel that is momentarily at rest with respect to the sphere. Okay, they're in contact. They're pressed together. Okay, there's some normal force, between them, and so there's a Fs maximum, right, and all that kind of stuff. Okay, so now what's happening is the guy is revving the engine. He's using the engine on the way up. A torque is applied to this wheel. What that's doing is it's taking that chunk of rubber and trying to push it this way. There's a force this way on that chunk of rubber. And if there were no friction, then the wheel would spin like that. It would spin. Okay, but because we're assuming that we're maintaining traction, okay, then these two surfaces are at rest with respect to each other. The atoms in the chunk of rubber that are touching the road, those atoms are touching atoms in the road. Okay, they're against each other like this. Okay, so this chunk of rubber goes, it tries to push this way, and so it takes the atoms in the road and pushes them this way. Remember, all matter is basically little chunks, particles of matter connected by springs. Okay, and so the atoms in the bottom of the tire, they're in contact with the atoms in the sphere here, and they push on those atoms this way. But those atoms are like little springs, and so they get compressed this way, and so then they push back this way. A compressed spring like this pushes back on you this way. So the atoms in the road get shifted a tiny bit this way. Okay, the road is very stiff, or the steel is very stiff. Okay, only a very tiny shift is required to exert a large force that way. Okay, so the atoms in the road actually apply a force that way on the rubber. Okay, and so there's actually a force that way on this motorcycle. Okay, so the sphere, so the rubber is exerting a force that way on the sphere. The sphere is exerting a force that way on the rubber and hence on the bike. Okay, so that's very important. So on the way up, there is a force of static friction in this direction. Up like that. Okay, very good. Yeah. Okay, so I think that's all I wanted to say about that. And what else? Okay, so now let's actually solve. So what we're saying is, because the speed v is equal to a constant, so this is sort of part A, I guess we'll call it. So part A, we'll say because the speed v is equal to a constant, remember that the velocity has two parts to it, a magnitude, which is the speed, and a direction. Okay? And so when we say that when the speed is constant, it means that there's no acceleration in the direction parallel to the motion. There's no force, there's no net force in the direction parallel to the motion. Okay, that's basic circular motion. So v is equal to constant implies, it actually is the same thing as, the parallel component of acceleration tangential to the circle there in the direction of the velocity, that's equal to 0. Okay, which tells you that when you add up all of the forces, okay, and you take the component parallel to the motion, that's the velocity there, that better equal 0. Okay, so then we look at this and say, let's add up all the forces parallel to the motion. Well, there's a force Fs directly in the direction of motion, and there's a normal component perpendicular. We can ignore that. And what we're interested in is the component of the weight that is parallel to the direction of motion. It's actually pulling back. Okay, weight is basically pulling back, trying to slow you down. The force of static friction is pushing forward, trying to speed you up. And so the two of them have to match so that your speed remains constant. Okay, that's crucial here. Okay, so what does this mean? So we need to figure out this angle. And so to figure out which angle here is theta, just imagine when theta here goes to 0, then which angle goes to 0? Well, then this weight, this guy will swing down, and the weight will always be just straight down, and so that angle will go to 0. So when theta goes to 0, that angle goes to 0, so this must be the angle theta. Okay, so that's great. And so what we're interested in is figuring out what force of static friction is required so that the net force in that direction is equal to 0. So there's Fs in that positive that direction, and then there's the component of the weight, which is in that direction of motion. So this is the hypotenuse, so the weight times, let's see, the weight times cos theta will give you that projection on the triangle. The weight times sine theta will give you that projection on the triangle. And that's what we're interested in. So weight times sine theta better equal Fs in order for there to be no net force tangential to the motion, and so the speed remaining constant. Okay, so let's write that down over here. So we get that the magnitude of the force of static friction, or F force of static friction, is the weight times sine theta. Okay, so this is a very important equation. Okay, now what we're going to do is we're going to see whether this equation makes any sense. Remember, at every step along the way, you're trying to see all partial results. Do they make sense? Because physics is not about just, math is super important, but it's not just about the math. It's about understanding the physics, what's really going on. Okay, so let's see what this equation is saying and see if it makes any sense. Yeah, okay, so let's draw a sphere down here, circle down here. Yeah, let's put it right here. Okay, so remember, theta equals 0 is down here. Theta equals 0 degrees is down here. Sine of 0 is 0. So this equation tells us that the force of static friction when the motorcyclist is passing through here is 0. Okay, you don't need to rely on static friction at all to maintain constant speed as you pass through this point. And why is that? Because if this circle were sort of unrolled to be a straight line, if we was moving along a straight line like this, with constant speed, you would need you wouldn't have to apply the engine or the brakes at this point to maintain constant speed. Okay, so Fs is equal to 0 down here. No static friction is required, engine or brakes at this point, in order to maintain constant speed. Another way you can think about this is sort of if you're coasting, well, you're going to be going fastest through the bottom and slowest through the top. So this is a minimum maximum. Wherever you're down at the bottom here, this is a little bit slower, that's fastest, that's a little bit slower. So on both sides, that's a maximum. And so the slope of the speed, the change in the speed is 0, the acceleration is 0. So you don't need a force of static friction. Another way to look at that is you've got a weight pulling down, you've got a normal force pushing up, and that's what you want. You don't want any force in that direction, so there can't be any force of static friction in that direction or that direction. Okay? Let's look at theta equals 90 degrees. So we come around like this, he's gone up. Now he's at 90 degrees, he's at the equator point. So that's 90 degrees. Okay, and this thing says that the force of static friction is, sine of 90 is 1, so the force of static friction is plus W. So the force of static friction we're measuring in that direction, counterclockwise. So we say, I should actually make a note of that. This is force of static friction is counterclockwise, CCW, counterclockwise around the sphere. This is the positive direction around the sphere. Okay, so this just says, yep, the force of static friction is positive the weight, which means it looks like this. And you say, does that make any sense? Well, yeah, it makes sense, because again, if you take that circle and you unwrap it and make it a straight line, and then you ask yourself, well, okay, so here's this guy rolling up, driving up this vertical wall here. Okay, and so what are the forces acting on him? Well, there's weight trying to slow him down, and so he's going to need a force in that direction from the engine equal to his weight. Okay, so that the weight and the force of static friction exactly cancel. So at this point, there's no net force in that direction, so there's no change in his speed in that direction. Now, of course, there's always an acceleration this way and a force this way, but and that's required because this isn't a straight line. It actually bends into a circle, and so to bend it into a circle, you need an additional force perpendicular. But in terms of the forces tangential to the circle, you want those forces to be zero at every point. Okay, and so you want the force of static friction to cancel the weight at that point. So now we come up to the top. So this is theta equals 180 degrees. Okay, so sine of 180 is 0, and so it says that the force of static friction required to maintain constant speed at the top is equal to 0. So again, you can look at it either as what are the forces that are acting. At the top, there's a weight pulling down, straight down, perpendicular to the circle, and there's a normal force pushing straight down, also perpendicular to the circle. So those two forces alone are perpendicular. You don't want to add a force this way or this way because that would be changing the speed. Or another way to think about it is if you were coasting, your minimum speed would be at the top. This is a little bit big. This is some speed. This is a little bit lower, and this is a little bit bigger again. So it passes through a minimum. And so when the speed passes through a minimum like that, the slope of the graph is 0, the acceleration is 0. Okay? Great, we got that. And now comes the interesting one, or most interesting case. This is 270 degrees. So at 270 degrees, sine of 270, this is 0, 90, 180, 270. Sine of 270 is minus 1. So the force of static friction is negative the weight. And this force of static friction is measured in this counterclockwise direction. So that's counterclockwise, and it's the negative of that, so it's up. So the force of static friction is negative the weight. And why is that? Well, that's because on this side, you're using the engine. On this side, you're using the brakes. Here, you're using the brakes. Okay, so let's go, suppose you're like here. Let's draw the wheel again. And this wheel is rolling along like this, okay, as he goes around, okay? And remember, we're talking about static friction here. Every time a chunk of rubber hits that, hits the road here, hits the sphere, there's no sliding that happens, okay? Now, normally the wheel is turning this way, like the wheel is turning this way, okay? So if it's turning this way, if you apply the brakes, what you're doing is you're exerting a torque or a twisting force the opposite direction. So applying the brakes, applying the throttle tries to twist it this way. Applying the brakes twists it the other way, exerts that twisting or torque the other way. Okay, and so this little chunk of rubber here, that's momentarily in contact and at rest with respect to the sphere at that point. Okay, the torque is that way, so that rubber is being pushed down like that. But it's in contact with the atoms of the metal, so they're being pushed down. So like little springs, they get shifted down a little bit. Like springs, they push back up. And so the atoms of the road push that way on the chunk of rubber. And that is the brakes. So that keeps you from speeding up. Just, if you're just coasting, you're going to naturally pick up speed. Well, this is what prevents you from picking up speed and thus able to maintain constant speed. That's that. Okay? Very good. So this equation makes perfect sense. Okay, so we know that we're right about that. Now, I want to say this is super important here. So this equation says, it tells us what force of static friction is required to keep the bike moving around at constant speed. Whether or not that's achievable is a totally different question. Because remember, we have this equation. We don't know what Fs is until we solve Newton's equations, and we did. Here we solved Newton's equations. We said, well, the force in that direction must be equal to 0. That's an F equals ma type problem. We solved it, and that told us that the force of static friction was equal to that. Okay, and then what we need to establish is that this is what's required, okay, for constant speed. But is it achievable? Well, whatever that is, better be less than or equal to Fs maximum. Okay, And we have a simple formula for Fs maximum. It's mu s times the normal. So I should mention here there's a coefficient of, very important, there's a coefficient of static friction between the bike tires and the metal sphere. Okay, so this is the central equation that we're going to look at. That inequality, and when we crank this out, it's going to say, oh yes, in order to get around that sphere with constant speed, there's a minimum speed. You know, the speed must be greater than or equal to something, okay, to get around. That's where that's going to come from, okay? But anyways, like I always say, whenever you're doing this kind of a problem with static friction, you always write down this equation. You don't know what this is, and you don't know what this is until you solve some of the forces of mass times acceleration. We've looked at one component, the component tangential to the velocity, and we determined what Fs is. So now we know this guy. Next, we're going to focus on what is the normal, and then we're going to plug it into this equation and figure out some interesting stuff. Okay? Okay, so now let's look at the second consequence of V equals constant. So we'll label that B here. So speed equals constant means that, as we said here, there is no parallel component of acceleration, so no force in the direction parallel to the motion. So there's only a component of force perpendicular to the motion. That's, of course, the centripetal force. So V equals constant tells you that when you add up all of the forces, there can't be a parallel component. There's only a perpendicular component. And so that's, mass times the perpendicular component of the acceleration. And if you're in uniform circular motion, constant speed, radius r, we know that this is mass times the magnitude of the centripetal acceleration is v squared divided by r, and the direction is directed radially inwards towards the center of the circle, okay, at all times. Great. So let's actually work this out. So we will take, at this point, and at any point here, we'll take the direction toward the center to be positive. So what is the net force towards the center here? We already showed that the net force in the direction parallel to the motion is 0. What's the net force in that direction towards the center? Well, the normal force is acting directly towards the center, so that's N. Okay, and then the force of static friction has no component in towards the center. The weight has two components, this and this. This component of the weight is in a direction directed away from the center, so there's a minus sign. And what is its magnitude? Well, it's the full length of the vector multiplied by cosine of theta to find the projection on that line. Okay, weight times cosine of theta. So that's the net force directed towards the center. And that is supposed to equal mv squared divided by r from here. Okay, and so then we can solve. We're going to solve for n. So n then is equal to mv squared over r, and then take the negative w cos to the right-hand side, positive w cosine of theta. Okay, so I just wanted to sort of remind you here that this is the main equation that we are interested in solving and looking at. This is all the interesting physics is in here, okay? But we don't know what Fs is, and we don't know what N is. The only way we get those is to look at the dynamics equation. So solving F equals ma in that axis, along that direction, told us what Fs was. Now, having solved F equals ma along that axis towards the center of the circle, we got what N is. Now we know what Fs is. Now we know what Fs is, and we know what N is. We plug them into this equation and see interesting things happening. Okay, but before we jump into that, I want to make sure that this equation makes sense to you. So I'll remind you of stuff you've probably seen in high school before, but it's a good reminder. Okay, this is important to understand this stuff. So let's plug in different values of theta. Let's say theta equals 0. In fact, I'm going to draw the circle first. So here is the circle that the motorcyclist is going around, and we're interested in what happens at this point. So theta is equal to 0. And so that tells us cosine of 0 is 1. It tells us that the normal force is equal to mv squared over r plus w. Okay, let's see if this equation makes sense. Well, so first we imagine that the motorcyclist is not going around the circle. He's moving with speed v along a horizontal flat road like this, and so then the motorcyclist has some weight, obviously, which is compressing the atoms in the road, and so like little springs, they're pushing back up, and so there's a normal force equal to his weight. Normal is at least equal to the weight. Okay, so that's his weight. But then that normal force so the sphere has to push harder than just his weight. Okay, because not only is he just going level like this, he wants to curve up like this. And to curve up like this requires an acceleration up. Okay, so as he's moving along this curve, he's moving upwards faster and faster and faster. He's accelerating up. At this point, he's accelerating up. So there has to be a force pushing up. Okay, and what is that force? Well, it's just the force required to move around in a circle like that. So it's an mv squared over r. So we have to add to that an mv squared divided by r. And so then the total normal force is bigger than just the normal force that would be exerted if you were on a flat road. There's an additional centripetal component required to bend his trajectory into a circle. Okay. Yeah, I think that's pretty much all. Oh, wait a minute. I want to also talk a little bit about apparent weight. Oh, also I want to say this. So when you look at this, this is the force required to bend his trajectory into a circle here. And so you can see that if his speed increases, maybe you double the speed, that centripetal force has to increase by a factor of 4. And why is that? Because if he's going faster, then he's going to go up like this a lot faster. It's going to require greater acceleration in the vertical direction, and so greater force. The sphere's going to have to push even harder on him to get him to whip around very quickly. Okay? If the radius of this circle, now it's drawn small, suppose it's much, much bigger, then this becomes much more of a gentle curve upwards, and so the acceleration in the up direction at this point is less, and so it requires less force. So when r is bigger, that centripetal force is less, and so on. Okay, so it's good to understand that kind of stuff. I want to introduce a little bit of terminology here that's common. There's this thing called apparent weight. Apparent weight. How do you spell apparent? Yes, apparent weight. Okay, so the apparent weight is weight with a little subscript a indicating apparent, and that's not equal to the weight. It's by definition, it's equal to the normal force. Okay, so the normal force that the ground exerts on you, okay, like right now, I'm standing on the ground, the normal force is just equal to my weight. So my apparent weight is equal to my actual weight, okay? But as this guy is whipping around here, his normal force is bigger than just his weight. His normal force is weight plus this, so his apparent weight is larger. He's actually feeling extra g forces, so to speak, okay, as he's being accelerated up more than just by his ordinary weight. So N is, so that normal force here, we're going to factor out the mass m, because weight is equal to mg. So mg is the weight, plus factoring out the mv squared divided by r. Okay, we have that. And so his weight is greater than, or he's experiencing, g forces when his speed is 0. The number of g forces he experiences is just 1g. Okay, but if we say, for example, that v squared over r, suppose that that's equal to 3g, okay, then it means that his apparent weight, is equal to m times g plus 3g. And so actually, he's experiencing 4 g's of acceleration, okay? Yep, as he whips around the bottom. So he feels extra heavy. It's not just his regular weight, he feels extra heavy. And then another 3 g's worth of acceleration. So m times 3g, an additional weight that he feels. That's his apparent weight is larger as he comes whipping through the bottom there. Okay, great. Now let's look at what happens on the sides. Okay, so let's look at this point and this point over here, say this point. Okay, so now in this case, theta is equal to 90 degrees or 270 or minus 90. So theta is equal to plus or minus 90 degrees. Okay, cosine of plus or minus 90 degrees is 0, so that term drops out. And the normal force is just equal to mv squared over r, and that's just a pure centripetal. Okay, Nothing else going on with his weight or anything, because remember, when you're at this point, if we look at the vertical forces that are acting, there's a weight pulling him down, there's a force of static friction because he's revving his engine, and so there's a force of static friction this way which cancels the weight, so there's zero net force at this point in the vertical direction. And so all he needs is a force in the horizontal direction equal to this mv squared over r. I'll draw it the same length. There's an mv squared divided by r for both of these. Okay, just required to bend him into a circle. Another way to look at it is, carrying on with this theme of suppose at this point you were moving along, say, a vertical road here. He's drifting along a vertical road here. Well, there would be, in order to cause him to change his direction of travel, would require exactly a force mv squared over r to curve like that at that point. Okay, so yeah, I think that's all I want to say about that. Yeah, there's no additional weight to support. Okay, and then the last case is when the motorcyclist passes through the top of the sphere. Okay, so now we have theta is equal to 180 degrees. In fact, I'm going to write it up here because we're going to need a little bit more space. Okay, so now we're talking about theta equals 180 degrees. Okay, when theta is 180, cosine of 180 is -1. So it tells us that the normal force is m v squared over r minus the weight. Okay, or we can rewrite this as m v squared over r is equal to the normal plus the weight. Okay, so when you're at the top over here, the normal force is equal to mv squared over r. That's a vector that's this long. Okay, so it's an mv squared over r. And then you subtract the weight. That's the mv squared over r. And then you subtract the weight. The weight was this shorter one over here, so you subtract that guy. And so what's required here is a normal force. This is the weight. And this is the mv squared over r. And this is the normal force. Okay? So at the end of the day, the idea is that whenever you're going around a circle, it doesn't matter where where it is in the circle that you are, the net force towards the center must equal mv squared over r. When the motorcyclist is passing through the top, there's already a force directed towards the center that's helping him bend his trajectory. Because if he just were moving on this straight line like this here, like this, well then wait, he would just move on a parabolic trajectory like that. So there's already a weight causing the trajectory to bend like this down. But that's not quite enough. You also have to add some additional normal force, so that the normal force plus the weight adds up to mv squared over r. Okay, so let's collect these three diagrams and show them together in one diagram, so that we can get a really clear picture of what's happening. Okay, so at the bottom of the sphere, the normal force is maximum. So this is, say, n max. Okay, because you've got not just the mv squared over r, but the weight. And then on the sides here, it's just mv squared over r, so it's smaller. And then at the top, it's the smallest, okay? Because the normal force is mv squared over r minus the weight. Here it's mv squared over r minus the weight. Here it's mv squared over r plus the weight. Okay, so this is n minimum. So if we were to go all the way around the sphere, we just smoothly connect. So a vector of length between this one and this one, so the normal force is maximum here, it becomes a little bit less here, becomes a little bit less here, becomes a little bit less here, and becomes minimum here. And then it starts to grow again, grow, and is maximum here. So that's what the normal force looks like. That's what this equation is telling you, the normal force, as a function of the angle theta. Okay? Now, what's really interesting about this is, say, if you look, say, at the top here, if you look at this equation, the normal force is this minus this. Uh-oh, minus sign, that means the normal force could become negative. Okay? If the guy's trying to get around this sphere with too slow of a speed, okay, such that mv squared over r is less than his weight, well then at the top, the normal force is going to be negative. It's not going to point down that way, it's going to point up. What does that mean? Well, in general, you're in danger because cosine of theta is negative between 90 degrees and 90, 180, yeah, 91, between 90, 180, and 270, cosine of theta is negative over this whole top of the circle. So this thing is negative. So it's possible for the normal to go to 0 if the speed is too small. Okay, so let's actually just work out a simple example of this. So let's suppose, what example did I work out? So, for example, suppose that the normal goes to 0 at theta equals 120. So between theta equals 120 and negative 120. Suppose that the normal is negative there. Let's see what that means. First, let's work it out. So we say suppose that the normal force is equal to 0 at theta equals 120 degrees, plus minus 120 degrees. Okay, so let's work this out. So we say 0 normal force is equal to mv squared over r plus the weight is mg, times cosine of plus or minus 120 is negative a half. So, minus a half, right? And so then the m's cancel out here, and so we can solve, and so this tells us that v, the speed v, that would make the normal force go to 0 at 120 degrees is r times g over 2 square root. So r times g divided by 2 square root. Again, you can put some numbers in there. I think in my notes here I put some numbers in there. If r is like 3 meters, the radius of the sphere is 3 meters, and his speed is 4 meters per second or whatever. For a radius of 3 meters, you plug that in there, and then the speed is 4 meters per second, 14 kilometers per hour. At that particular speed, for that size of sphere, at that particular speed, it will turn out that, this is the interesting part, it'll turn out that at this point over here, and at this point over here, n goes to 0. So n is largest over here, and then it gets smaller, and then it gets smaller, and then it gets smaller, and then it drops to 0 here, and then it's negative here, and it's negative here, and it's negative here, 0 here, and then it gets positive again, and larger positive. So here the normal force is positive, and everything is fine. He can just ride around like this. But to say that the normal force becomes negative over this, it means that he's going too slowly. He's going too slowly to whip around and push outwards on the sphere as he whips around, so the sphere pushes down on him. What's happening is he's going too slowly. His normal force drops to 0 here. The normal force actually has to pull up on him. So it's like those roller coasters, right, that have two wheels, one on the top of the track and one on the bottom, okay, as they're going around the track. So on this part of his trajectory, the wheel on the inside is being pushed on this way, okay? But then when the roller coaster gets too slow and you're going upside down like this, then you have then it's the wheel on the outside of the track, which is hanging down like this, and the normal force is coming from the outside and pushing up on that outside wheel. Here it's pushing up on that inside wheel. Here it's pushing up on that outside wheel. Now, if he doesn't have that outside wheel, then what happens is he goes, at this point the normal force drops to 0, and then he enters free fall. He loses contact with the sphere. So he starts with this speed over here, but he doesn't go around this circular track. He enters a parabolic trajectory. Boom, crash and burn, fire, death, right? This is like, physics is like life and death, right? If we don't get this calculation right, those guys are gonna die, right? So yeah, there you go. so that's what it is. Let me see. So there's some talk here about the minimum speed to prevent this from happening at the top and all that kind of stuff. I'll just leave that for you to look at in the notes there. That's not super important. Now what we want to do is we want to get back to really just part A here. So what we did is we said this is the main equation that we want to look at. Okay? We want to make sure that we want him to maintain constant speed around this vertical loop. And that requires that the force of static friction be this. Okay? But, and the normal force be this. But in order to do so without the wheels slipping, without breaking static friction, we need to ensure that this thing is less than or equal to mu s times this thing. Okay? So let's see, how much room are we going to need? So let's erase this stuff down here. Let's keep the normal up there. Let's get rid of this stuff. Let's plug these two things into there. So Fs, this is what it needs to be, W sine theta. Is this actually achievable? Well, we have to ensure that this is less than or equal to mu s times the normal. So that's mv squared over r plus weight cos theta. Okay, so we have that. And so, you know what, I'm just going to let you solve this equation. What you're solving for is v squared over r. So this tells you that, in fact, maybe I can fit it in here. This tells you that v squared over r, and this is sort of the central result here, that v squared over r, if you solve this algebraic equation for v squared over r is bigger than or equal to some junk. And that junk turns out to be greater than or equal to 1 over the coefficient of static friction times sine theta minus cos theta times g. Now this is a really interesting result. Okay, so first of all, you look at that result and you say that that makes sense in the following way. If we say, suppose that the coefficient of static friction is really low. It's a pretty slippery surface, easy to break static friction. Okay, then mu s is small, 1 over mu s is large. And so it's telling you that when it gets less and less traction, then the speed has to be larger. So that's sort of an intuitively obvious thing, and you can see it coming out of the equation. But let's look at it in a little bit more detail. You'll notice that the speed, the v squared, must be bigger than or equal to some number. But that number depends upon the angle theta. It depends upon where you are in that circle. Okay, so this is some function of theta. And so the worst case scenario is where this function of theta is biggest. Okay, that's what you have to, because if v squared over r is bigger than the maximum value of this function, then v squared over r will be bigger than that value for all values of theta, and then you're good to go. Okay, so what we have to do is we have to plot this function. So because mu s here is a variable, let's just set it equal to 1. So a typical value, just to get sort of a ballpark feel for this, typical value for coefficient of static friction is, let's say, 1. And so what we need to do is we need to ensure that v squared over r is greater than or equal to sine theta minus cos theta times g. We can also take the g down here. So we need v squared divided by gr greater than or equal to sine theta minus cos theta. And so, so let's plot this function. So what does sine theta minus cos theta look like? So this is a great example because it exercises your skill at graphing and drawing sines and cosines and sums and differences of those. Okay, so this is sine theta minus cos theta. And we're going to take theta, let's just take theta between 0 and 180 because the same thing repeats on that side. So between 0 and 180, and so 90 is here, okay? And this is plus 1 and minus 1, okay? So what you want to do is plot sine theta minus cos theta. So I'm sure you've done these plots in your high school math. So sine theta starts at 0, and then it goes up to a maximum value at 90 degrees, and then it goes down to 0 at 180. And so sine theta is a function that looks like this. Okay. Cosine theta starts at 1, goes to 0 at 90, and then is minus 1 at 180 degrees. But we're plotting the negative of cosine theta, and then we're going to add the two curves. So the negative of cosine theta starts at minus 1. When it passes through 90 degrees, it's 0. And when it hits 180, it's positive 1. Okay? And so now what we need to do is we need to add sine theta plus negative cos theta. And of course, the way you do that is you just look at every value of theta, just add the two values of the curve. At theta equals 0, we have 0 plus minus 1. So that's a point on the sum. Okay, at this point over here, we have at theta equals 90 degrees, we're adding 0 plus 1. That's just 1. At theta equals 180 degrees, we're adding 0 plus 1. So this point, and this point are on the curve. Let's look for in between. So maybe at around here, if you look, the value of this is some positive number, and the value of this is some equal negative number. So they'll add to 0 at this point. Okay, and over here, if you know sine and cosine of 45 degrees is 1 over root 2, this is 1. 1 over root 2 is about 0.7. So this height here is 1 over root 2 for both curves. So at this angle, which is exactly between 90 and 180, at 135 degrees, at that crucial angle there, the value of sine theta minus cos theta is 1 over root 2 plus 1 over root 2 is 2 over root 2, which is the square root of 2, which is about 1.4. If that's 1, that's about 1.4 is about here. And so we have these points in the curve, duk, 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 duk. So let's connect those points with a smooth curve. So it looks like this. In fact, let me just do it in a different color to make it a little clearer. So it comes up like this. And then it peaks through here. Okay, something like that. And so what's interesting about this equation is saying that v squared over r has to be greater than or equal to this number. Well, it depends. So you can go without slipping if your angle theta is, say, close to 0. If you're close to the bottom of this circle here, then this thing on the right-hand side is actually negative. And of course, for any speed v, you're squaring it. This is a positive number. A positive number is always bigger than or equal to a negative number. So when mu s is equal to 1, you run into no trouble whatsoever between 0 and 45 degrees. So between here and here, no trouble whatsoever. Okay? But then between 45 and 90 degrees, so in here, you start to realize, ooh, wait a minute, I'm going to have some, non-zero speed. I'm going to have to be moving, faster than a certain amount to get through there. And then if you go between 90 and 135, it gets even worse. And the worst case is reached right up here. Okay? So let's call this angle theta star. Okay? So at this angle, this is the worst case scenario, okay, for slipping, okay? And that's because, if you think about this a little bit, this is kind of cool. If you think about this, let me just draw it this way. So here's our sphere, our circle, I mean. Okay, 135 degrees, this is 0 degrees, 135 degrees is right up here between 90 and 120. So right at that point there, that's our theta star. That's our critical angle at which we have the worst case scenario. What are the forces that are acting? Well, there is a weight that's pulling down like this. There is a force of static friction which has exactly the same length as the projection of the weight tangent to the circle here. So it's that length right there. That's the force of static friction. So that force of static friction plus weight in that direction cancel, and there's no net force tangential to the circle, and the speed is constant. Okay, and then there's also a normal component here. Now remember that the normal component is largest here and smallest here. The normal component is getting always smaller, 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 and so Fs max is getting smaller, 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 smaller. It's really smallest over here. Okay. Okay. So this is the critical point at which slipping is most prone to slipping at that point. Okay. So that's kind of cool. So then let's actually figure this out. We have the worst case scenario is at 135 degrees. We figured that out here. And so let's then solve. What is this v squared over gr when we put in 135 degrees? So it says that v squared over g times r has to be greater than or equal to sine of 135 degrees minus cosine of 135 degrees. Okay, and so sine of 135 degrees, so that's on the circle here, 135 degrees on a unit circle is 135 sine is plus 1 over root 2. And And then cosine of 135 degrees is negative 1 over root 2. So it's negative 1 over root 2, or subtract negative 1 over root 2. So that's 1 over root 2 plus 1 over root 2 is 2 over root 2 is the square root of 2. Okay, so then we can solve this equation for v. So it says that v then is greater than or equal to, take the square root of 2, multiply by gr, and then take the square root. Okay, so that's interesting. So the speed has to be bigger than or equal to this. And so let's actually plug in a number. So let's suppose that, that the radius is, say, 3 meters. These are actually usually pretty small spheres that they whip around in. Let's just put in 3 meters just for fun. And so if you do that, it tells you that the speed that the motorcyclist must whip around has to be at least equal to, well, you know R and you know G, so you just plug in that number, and this thing turns out to be 6.5 meters per second. Okay, or you can convert that to kilometers per hour. That's about 23 kilometers per hour. Okay, so if you're going faster than 23 kilometers per hour, no problem. You can go around at that constant speed without the tires losing traction and starting to spin. But if you're going slower than that speed, then you're going to run into trouble. And the first point you're going to run into trouble is right here. That's the worst case scenario. Okay, that's really cool. So we started with a very simple problem here, just motorcycle going around, you know, in a vertical loop with constant speed. But then we had to think carefully about, yes, what is the force of static friction? And how does that work? Why is it up when you're using the engine? And why is it up in this direction when you're using the brakes and all that kind of stuff? At the end of the day, remember, this is the key equation. And you don't know Fs and n. You get those by solving some of the forces, mass times acceleration. You plug those into that equation, and then you get an equation that tells you something about the speed. So the speed must be bigger than or equal to something. And then we had this interesting complication where the speed must be bigger than or equal to something, but that something depends upon the angle. We're trying to maintain constant speed, so we just need to look for the worst case scenario. So we plotted this function. There it is. The worst case scenario is at 135 degrees. Okay, and so that tells you what that constant speed must be. It must be greater than or equal to that. Okay, and then you crank it out, and you get a number that's pretty reasonable. I think I worked out the period here, didn't I? No, I didn't work out the period. Anyways, you can work out the period, how quickly they come around, and see if that's reasonable. Okay, so anyways, that was I like this example. This is my favorite examples. All right.